Hey y'all, this is Miss Henze checking in with our earthquake notes for the week. So we're going to go ahead and start with the vocabulary that we did in class. I'm just going to go ahead and put these in the correct places, and I would like you to take the moment to make sure you have them all copied into your notebook the way it's supposed to be. This would be a great time to use the pause button to make sure that you have them all recorded. You can either choose to put them in your vocabulary section of your binder, or you can put them in your Cornell notes for class. So here we have the first type of fault that we talked about. The first one is the strike-slip fault. And as you can see, it says here vertical or near vertical fracture on the earth where the ground has shifted horizontally. If you stand on one side of the fault and the block opposite you shifts the left, the motion is termed left lateral. As shown in this example, if it moves right, it is right lateral. So I'm going to hit play, so watch what happens. You can see where the fracture is, and then the earthquake happens. Watch what's happening to the river as the block of land shifts. You can see that there's the fault plane here, and that this is again was a horizontal motion. The next fault that we are going to be looking at is the normal fault. So as you can see, it has a dip. It's also called the dip or slip fault. The block above the fault, the hanging wall, moves down relative to the block below the fault, which is the footwall. This fault motion is caused by tensional forces and results in extension. So I'm going to hit play and watch what happens. You can see that here's a fault line, and that the hanging wall has moved down, and the footwall stayed in its place. Now the reverse fault is exactly the opposite of the normal fault, in which the hanging wall moves up relative to the footwall. This is caused by compressional forces. Now we talked about compressional forces a little bit in class as well, and it results in the shortening, and this is also called a thrust fault. So watch what happens. Again, you see the earthquake and the hanging wall moving upwards, and the footwall staying in its position. So here we have the causes of earthquakes. The first one is that when the rocks on either side of the fault try to move, the friction allows elastic energy to build up. Now, elastic energy is kind of the key here. When you think of elastic, you tend to think of rubber bands. Or the elastic in your waistband of your gym shorts. Okay? So what happens is that elasticness needs to return to its normal shape. So that's a big key. And so elastic energy, when things are trying to move and there's lots of friction, that the elastic energy tries to push the rocks back to where they were, but they continue to keep moving. And eventually you have that the elastic energy is great enough to overcome the friction and the rocks move or they slip. It's kind of like when you press your hands together really hard and you try to move one, and then you can feel the pressure, but eventually it will slip. And that's basically what happens when you have an earthquake. Now, when the rocks move, we get these types of waves. Now, these are not waves from the water, but they are more waves of how things move. And when you think of waves, you typically think of this up and down, up and down, up and down kind of movement. Well, that doesn't always happen. So it's important for you to remember that they move outwards from the focus, now it's a vocabulary word, where the actual rock slips, and then it moves outwards similar to the ripples in the water, just like the picture shown here. And here is also another example. Here you can see the focus down here, and then you can see the rings or like the ripples of the shock waves moving out from where the earthquake happens. Now, the earthquake right above the focus is the epicenter, which is where the highest level of destruction is usually found. And that the further away from the epicenter you get, the damage decreases. So this is where the strongest waves hit. Okay. And then the last part, and then this is the types of waves. So you have the P waves, which are compressional waves. And so remember, compression is like taking a large marshmallow and then squeezing it down so it's the size of a small marshmallow. So you're compressing it. You're filling it into a smaller space. So your P waves move this way. Let me get the pen over here. So your waves move this way, and you can see this compression area here where the lines are a little bit closer together. So they kind of make you bend, and then you're going to want to snap back. And then here is your normal S wave, your normal wave looking thing. And so these are S waves. S waves are transverse waves. They're also called shear waves. And the P waves actually stands for primary because they are the ones that typically move faster. And the term that seismologists use to describe the way a wave moves is called propagate.
The direction of energy release. So a P wave is like this. I knew I'd do that to you. Manny is my friend.
Kind of died.
No, I didn't.
I wasn't prepared for that.
What's going on?
You've all been a P wave. Yay. Okay, wait, don't go anywhere though. So you've got a compressional wave experience. Something has hit you and you've bent forward and then elastically rebound. Okay, and then the energy of that, me shoving Maddie to the side, traveled through Earth material. Is this video?
Yep.
Way cool. Okay, is this like your ploy for extra credit?
No way.
Oh, well, it would work. Alright, so on being an S wave, a shear wave propagates by sliding and rebounding against rigid material. Okay, so when one slides, one hooks elbows if we're a rock. Okay, so we're gonna hook elbows.
How am I gonna do this?
You know what? I need to let go of you. Danny's not sure she's up for this. Okay, so now we're going to slide past one another as rigid rock and see what happens and if we rebound.
That wasn't very good.
I'm the one with arthritic knees. Oh, yay! Oh, any injuries? Oh, okay. That was the worst. Okay, so you were a rock being a shear wave because once again you were able to slide past your partner and rebound. Okay? Shear waves in water. Now you're not hooking elbows. I shouldn't say water. I should say liquid. Now, the nature of the earth material is not such that we're attached to our near neighbor. So, a shear wave, Maddie's way relieved because now a shear wave in liquid. Now! excited. It doesn't really get much past Sean. Okay, so one more time, we'll do the P wave because that seems least dangerous, and we stood up. We should do one. You ready? So a P wave. Now it's a compression, and it's advancing in the direction of the energy release. You lost your enthusiasm. Team Awesome is over-energized. Okay, that's it. You have now been P waves and S waves.
So a tsunami is a large wave that happens when there is a earthquake underground. And so as you watch, you can see that this is a 3D simulation. Now, right here is where the earthquake occurred. So here is where you have some water being pushed upwards. And now, because the sea level is usually at the same level, that water that has been pushed upward has to be displaced and spread out along the rest of the ocean. And when that happens and that's when the large wave starts to move. So here is that displaced water, and it's continuing to move in a direction outwards from where the earthquake actually happened. And here you can see that the wave is still propagating away from the actual earthquake, and that as the ocean or the water level decreases, so as it gets shallower, you can see that the ocean floor is coming up. You can see that the wave is getting much larger and taller. So this is when you hear about a tsunami being a wall of water, it really actually is similar to a wall of water. And this is also what causes like the sea level to come out before the actual tsunami hits the coastline. And as you can see, when the tsunami hits the coast, it is very destructive. And now, so let me just let the credits roll real quick. And then on the next slide, we have a before and after image. Now, a lot of the death and a lot of the destruction, I should say, is caused by the actual water itself, because most buildings are not built to withstand a 30-foot wall of water. Now, a lot of the death that occurs is because of the aftermath and because of the debris that's in the water. So if a person is caught up in a tsunami and they're a really good swimmer, they could get, their bodies could be really bombarded by a lot of the debris in the water. So you have lots of pieces of buildings, cars, boats, I mean, you name it. Anything that was around when that tsunami hit is going to be floating in the water. And so as the water recedes, you can go from the top picture of all these buildings and trees and roads to this bottom picture where all you see is like brown, and most of what you can see here is the debris. You can also see that part of the coastline from here to here and also down here is still either underwater or was washed away a little bit. And that often happens because the coastlines are not as stable as the inner parts of the island. Death can also eventually come from, lack of sewage treatment. So usually if there's a lot of damage, the facilities that treat sewage are not able to do that. Therefore, there's contamination of the groundwater, and there's no fresh water for people to drink. And there's not a lot of food around because everything has been destroyed. So that's why a lot of people will really focus on areas that have been hit by tsunamis, because those people that have survived that huge natural disaster are in really a lot of need of help. And so this is a part that we did not get to in class, but here is the this is how seismologists will measure an earthquake, and it's called a seismograph. And what the number that they assign to a seismograph is called the magnitude. And you can see that there's like these drums of paper here and lots of little squiggly lines on it, if you can see it. But what happens is that there's like a little marker that will shake when an earthquake is registered. And it's kind of interesting to see what happens and how far away these things happen. So you may be aware of the Richter scale, and the Richter scale is the levels that seismologists give to earthquakes based on how strong they were. And so it's important for you to understand that when you go from level 1 to level 2, it's not just going up by like one little bit. It's actually 10 times stronger. So this is an exponential equation. So what happens is that for each level it goes up 10 times. So you have a 1, and going up to a 2 is 10 times stronger. Going up to a 3 is 10 times stronger than that, which means that it would be 100 times stronger than a level 1. Now, usually people do not see or feel anything lower than a 3 or a 4 because our bodies aren't able to detect that small amount of movement. But when it starts getting into the 5, 6s, you can really start to see it. And then 7, 8s, 9s. I don't know that we've ever had something above a 10, but we came pretty close with that magnitude 9 earthquake off the coast of Japan, and I believe the one in Haiti was pretty close as well. So you can see how often they occur, and a 9 is about yearly, about every 300 years, and that's considered very severe. The movement happens a lot. And so that way you can, if you're looking at a magnitude 9 earthquake, there's going to be a lot of destruction because the ground moves a lot and a lot of the buildings end up collapsing, and that's where people end up dying, and that's where the issues tend to happen. So one thing that you'll notice is that when you were doing your research about the different levels of earthquakes, we saw some that were, in the 6 and 7 range that had hundreds of thousands of people that died. Now, the big issue is that when you have these 6 and 7 magnitude earthquakes, now it's moderate to major, and it doesn't happen nearly as often, but you have some pretty sudden movements, so strong to severe. But you'll notice that as we increase our technology, scientists and engineers have begun developing building codes to ensure that a building will stand up to a stronger earthquake than what they used to. Now, you can have a magnitude 9 earthquake in a really unpopulated area, and there won't be a lot of damage or destruction or death. Sorry, that was my son running around. And so if it happens in a highly populated area such as Haiti or Chile, this is when you start to get a lot of people that are getting trapped in buildings that have fallen and death that occurs. So as the scientists and engineers continue to develop different ways to build buildings to withstand earthquakes, we will start to see fewer deaths as well. And so that is the end of our slideshow for earthquakes, and we'll be looking a little bit more at maybe some building techniques that they will be using to make sure that buildings withstand some much larger earthquakes in the future. So please make sure that you ask Ms. Henze any questions if you have them, and make sure that you are taking your notes as needed. You can always go back and rewatch this as needed, especially if you were absent. So make sure that you do that, and I will see you in class.